Now we will see the electric field due to infinite line charge. So we are already seen what is the line charge, and that line length is infinite, and that is oriented on the z axis. This is our assumption. It can be oriented on any axis or it may not be oriented on any axis. So in this particular derivation we are assuming that the infinite line charge is oriented on the z axis. So like this I have taken. So x axis is coming out of the screen, this is y axis, this is z axis. On the z axis where z is changing from minus infinity to plus infinity, on that particular z axis the infinite line charge is available, and we assume that infinite line charge is having the line charge density rho L, and it is uniform line charge density. Uniform is nothing but everywhere the charge density is same with respect to z. Okay. Then what we need to do? Previously we have calculated the electric field at certain point or in some position in the space due to the point charge. Now again same thing, we have to calculate the electric field at some position due to this infinite line charge. So we will assume that our observation point, that means where we are finding the electric field, that is said to be observation point. That observation point is available on the xy plane, and we will solve this one in the cylindrical coordinates. There is a reason for solving this particular electric field concept due to the infinite line charge in the cylindrical coordinate system, because you need to select the coordinates according to your problem. We have to follow the symmetry. In our previous classes I have told you about that one. We need to select the coordinate system in such a way that the symmetry has to be followed by the electric flux lines. Then the calculation will be easier, otherwise it will be difficult. That means more number of integrations have to be done if you use another coordinate system which is not having the symmetry with respect to the electric field lines generated by this particular infinite line charge. And before starting the calculation itself, we will see what is the components available in the electric field. Since already I said that we are calculating this one in the cylindrical coordinates, electric field at one observation point on the xy plane can be in this particular form. E bar is equal to E rho A rho cap plus E phi A phi cap plus E z A z cap. So it may contain the rho component, phi component and z component. Now we will analyze something without calculating anything, just you observe here. Changing the phi is nothing but what? Phi is equal to 0 is nothing but we are on the xz plane and we are seeing the infinite line charge which is oriented on the z axis. Phi is equal to 30 degrees. So you are in the first quadrant in between positive x axis and positive y axis, and you are observing the z axis. Again it is looking similar, whether you are at phi is equal to 0 or whether you are at phi is equal to 30 degrees, since the line is of infinite length, it is looking same. Like that you take different phi values, take phi is equal to 90, you are on the yz plane, and phi is equal to 270, phi is equal to 315, phi is equal to 360 again. For any phi value the infinite line is looking similar. That means by rotating around the infinite line charge, if you observe, it is looking similar because it is of infinite length. So that what we can able to do in the sense, what is the conclusion we can able to give means, with respect to phi there is no change in the electric field, or electric field is not containing the phi components. So simply we will remove this one. E phi component is not available because there is no change with respect to phi. That is the thing. Okay. The source is looking the similar, source is nothing but infinite line charge. For all values of phi the source is looking similar, the source is similar, so that it is not changing with respect to phi. Now we will see with respect to z. What is the change of z? Changing z is nothing but what? We have to move along the line charge. at z is equal to 0, you are on the xy plane and you are seeing the infinite line charge. If you see upside, that means you are looking at a positive z axis, you are observing the infinite line charge. If you see downside, that means if you see towards the negative z axis, again you will observe the infinite line charge. Now you take z is equal to 100, you see upside or downside, again it is looking similar. If you are at z is equal to minus 1500, again it will be looking similar. That means variation in z is not affecting anything. That means again E bar is not having the z component. Even you are changing the z, even you are changing the phi, the infinite line charge is looking similar. At every value of z, at every value of phi, the source is looking similar. That means it is following the azimuthal symmetry because of the phi in case of phi, and because of the z we can able to tell axial symmetry. So here two things are there. One is azimuthal symmetry in case of phi and axial symmetry in case of z. So that we can able to tell there is no E phi component, there is no Ez component in the electric field of this particular infinite line charge. So there is only one thing is there, that is E rho component. How it is possible? Changing rho is nothing but what? Moving away from the infinite line charge. Okay, rho is the perpendicular distance in between the observation point where you are finding the electric field and the infinite line charge. As we are moving away from the infinite line charge, we know very well about the force equation or the electric field due to the point charge. That is, if the distance is increasing, then the electric field or the force will be decreasing. So in this case also, because of that particular reason, we will assume that E rho component is available in the E bar vector. But clearly we can able to tell because of the azimuthal symmetry and axial symmetry, surely we do not have E phi component and Ez component, only E rho component is available. So now our job is to calculate this E rho only. Now we will enter into the derivation part. So we will assume that our observation point is available on the xy plane. On the xy plane z coordinate is 0. So the observation point coordinates are rho phi 0. So this is your observation point where we are finding the electric field actually. And instead of seeing the total line charge, instead of considering the total infinite length line charge, first what we will do in the sense, we will assume a small differential length. A small differential length we will assume, that is dl bar, length is a vector, so that dl bar, and the infinite line is oriented on the z axis, that is why dl bar is equal to dz az cap, the direction is along the z direction only, that is why dz az cap. At that particular dl, if the dl is shrinking to a point, then we can able to consider there is a point charge. So that point charge is given by dq, because of the differential length dl at that particular place, we can able to assume differential charge dq is there, and that dq is given by, since we are working with line charge, it is having the line charge density rho l. If that rho l is multiplied with dl, then you will be having the charge available in that particular dl. So dq is equal to rho l dl. This is what we have discussed in the charge configurations concept. So dq is in coulombs, rho l is coulombs per meter, dl is distance, that is again meters. So meter will be cancelled, coulomb is equal to coulomb you will get. So dq is equal to rho l dl we got, and dl is nothing but already we know that is dz. So dq is equal to, we can write rho l dz. So do not see entire infinite line charge now. Now it is about point charge only, dq is the point charge, and for the point charge already we know the equation of the electric field. Since it is a point charge, we are permitted to use this particular formula, that is dE bar is equal to 1 by 4 pi epsilon dq by magnitude of r cube into r bar. We are permitted to use this formula because dq is a point charge, so we can able to use. But in order to use this particular formula, we need R bar, and we know very well about the R bar. From the Coulomb's law onwards, so many times I have told that first we are interested to calculate the R bar only in every problem. Okay, if you are able to find the R bar, most of the problem was done. So what we need to do, we need to join the observation point and the source point. So by joining these two, we can able to get the R bar. Actually, electric field is along the line which is joining the observation point and the source point. So these two we have joined, and that is said to be R bar. And now already we have observation point coordinates, those are rho phi 0. Since that is available on the xy plane, z coordinate is 0, so that rho phi z coordinate 0 I have taken. What about source point coordinates? Now you have to be more careful. I can take the source point coordinates as 0, phi, z. Why it is 0? Because we are at, or the line charge is on the z axis, only, so that there is no radial distance, so that we can able to tell rho is equal to 0. That means the first coordinate in that particular source point is equal to 0. What about phi? Phi we will discuss later. And whatever the dq we have considered, the dq is available above the xy plane, so that certain amount of z value is there, that z value we have taken. Now we will consider the phi value. For example, we are discussing here two-dimensional polar coordinates, x axis, y axis I have taken, and this is the point where rho value is phi. Actually rho phi, each and every point on a surface can be represented with rho value and phi value using the polar coordinates. So phi comma 45 degrees, that is the point represented with the phi comma 45 degrees using the two-dimensional polar coordinates. Rho is phi and phi is 45 degrees. Okay. Then by making the 45 degrees is constant, if you reduce the rho value, what you will get? This point is representing 4 comma 45. This point is representing 3 comma 45. This point is representing 1 comma 45. The point nearer to origin can be represented with 0.00001 comma 45 degrees. If you observe one thing, as rho value is decreasing, phi value is not decreasing in that particular direction. We are interested to calculate the electric field along the line which is joining the observation point and the source point, so that whatever the phi value is there for the observation point, the same phi value we have to take at the source point. Okay, by using this particular explanation, you can able to understand that why phi is taken as the middle coordinate for the source point. Same phi we have to take, whatever the phi value is there for the observation point, same phi value we have to take, because it is in the same direction. You see here, in the same direction we are moving towards the origin. So in the same direction we are moving, in the sense we are making the 45 degrees is constant. So that same 45 degrees should be available at the source point also. That is the reason why we have taken the 0 phi z as the coordinates for the source point. So source point is at 0 phi z, observation point is at rho phi 0. Okay. What is the R bar? From starting onwards I am telling that R bar is nothing but observation point minus source point. So rho minus 0 is rho aero cap, phi minus 0 is phi, phi minus phi is 0, and 0 minus z is minus z az cap, and immediately we can calculate magnitude of R bar also, that is square root of rho square plus z square. You have dq value, you have R bar and magnitude of R. So substitute all these things in this particular equation number 1, so that you will be getting the differential electric field only, that is due to the differential charge available in the differential length dl. So dE bar is equal to 1 by 4 pi epsilon, dq is nothing but rho l dz by rho square z square whole power 3 by 2, because cube is available for the magnitude of R, power 3 will come, and by 2, root means 1 by 2, power is 1 by 2, and R bar is nothing but rho aero cap minus z az cap. So, like this we can able to take. And before going further, here what we need to do in the sense, whatever the diagram is taken previously, the same diagram can be considered like this also. The x axis coming out of the plane, like this also we can able to represent, and it is y axis, it is z axis, and it is 0 comma 5 comma z, just now we have seen that one, and there may be another point okay, below the xy plane at the same distance. That means if you travel z units below the x direction, then you will be leaving with one more differential charge in the differential length dl. Because of this one also, you are having the electric field at the same observation point. Our observation point is represented here on the xy plane, that is rho comma 5 comma 0, same observation point. Because of the first differential charge, this is the direction of the electric field. In which direction the electric field is there? You are moving downside and you are moving away from the infinite line charge. So, you are moving away in the sense you are moving in the arrow direction, you are moving downside means you are moving in the minus az direction. But because of the second differential charge which is available in the position 0 5 minus z, you are moving upside and right side. Since you are moving right side, that means you are moving away from the infinite line charge, you are traveling in the arrow direction. Since you are moving upside, you are traveling in the az cap direction. So, because of these two charges, if you consider, arrow direction is common, but az direction and minus az direction, these two will be cancelled to each other. That means resultant electric field will be in the direction of the arrow only. That is the thing we have to remember. Resultant electric field is in the direction of the arrow only. This is what we have told before starting the calculation only. The E bar is containing only arrow component only. That is the thing we have observed here. Okay. Then coming to the previous equation, okay, here again I will write that particular equation. dE bar is equal to 1 by 4 pi epsilon, dq is nothing but rho L dz by rho square plus z square whole power 3 by 2. Here rho arrow is enough now, because it is not traveling in the z direction. So, you no need to take the z component. So, this is enough for us. Now, we need to do the integration to have the total electric field. This is the just a differential electric field only. Due to the two differential charges, dq available at 0 phi z, another dq is available at 0 phi minus z. Now, if you integrate this one with respect to z from minus infinity to plus infinity, you will be having the E bar, total electric field at the observation point due to the infinite line charge. So, here 1 by 4 pi epsilon is constant, rho L is uniform, it is also constant, and rho is also constant, arrow is also constant. Because we are doing the integration with respect to z, the terms which are involving z are variables, remaining all are constants. So, integral dz by rho square z square whole power 3 by 2, and z is changing from minus infinity to plus infinity. Okay. Now, assume z is equal to rho tan theta, dz is equal to rho secant square theta d theta. Lower limit if you find z is equal to minus infinity, that means theta is equal to minus 90 you will get, because tan will become minus infinity when theta is equal to minus 90, and upper limit is theta is equal to plus 90, because tan will become plus infinity when z is equal to infinity, when theta is equal to pi by 2. Substitute all these things. So, you will be having E bar is equal to 1 by 4 pi epsilon rho L rho arrow cap integral theta is changing from minus pi by 2 to plus pi by 2, dz is nothing but rho secant square theta d theta by rho square plus z square. Z square is rho square tan square theta, rho square can be taken common, square and 1 by 2 will be common, so that you will be leaving with rho cube. 1 plus tan square theta is secant square theta, so you will be having secant cube theta, and here secant square theta will be cancelled. 1 secant theta is there in the numerator, sorry, in the denominator, and here rho, this rho will be rho square. So, rho square will be cancelled in the denominator, you will be having 1 rho. So, it is equal to 1 by 4 pi epsilon rho L A rho cap, and here what is the remaining thing? Rho is there in the denominator, since that is constant I am writing outside. Now 1 by secant theta, that is cos theta. Cos theta integration is sin theta, and limits are minus pi by 2 to plus pi by 2. Sin pi by 2 is 1, minus sin of minus pi by 2 is minus 1, that means from this you will get 2. So that 1 by 4 pi epsilon rho L by rho A rho cap into 2. So 2 ones are 2 twos are, that means you are having 1 by rho L by 2 pi rho epsilon A rho cap. This is our E bar. So proof is over. This is the thing. So this is the electric field due to infinite line charge at some observation point. Okay. E bar is equal to rho L by 2 pi rho epsilon A rho cap. So it is having only radial direction, that is having only A rho component, and it is proportional to the line charge density rho L, and it is inversely proportional to the distance rho, that is the perpendicular distance in between the infinite line charge and the observation point. These are the conclusions we have to remember.